Good evening to everyone. I welcome you all to this NPTEL tutorial session on IC engines and gas turbines. So my name is Tanmay Sharma. I'm a Prime Minister Research Fellow from Mechanical Engineering Department of IIT Patna, and I am assigned as a uh, TA in this NPTEL course series, IC engines and gas turbines. And today's lecture, we'll be solving a few problems related to gas turbine. And these problems, we have already solved a few problems in our previous session, but today's problems are a little bit advanced, a little bit requires a little bit more this problem solving skills. So we will learn about a lot regarding this problem solving of gas turbine problems, and accordingly we will gain more confidence on the gas turbine part, and by this we will end this open cycle gas turbine part. So let us move on. First, we would like to recapitulate what is the open cycle gas turbine. So in an open cycle gas turbine, what happens is that the air is sucked in into the compressor, and the compressor, it compresses the air. The compressor compresses the air to a elevated pressure, and the air in this compressed form will move into the combustion chamber, wherein fuel will be supplied, and the combustion will take place, due to which a huge energy will be supplied to the gas turbine, and this energy will elevate the temperature of the gas. Now this is not air anymore, and this is has become a gas, and the high temperature gas will then go inside the turbine, wherein the gas will expand and it will liberate its energy to the turbine shaft, which is responsible for rotating the shaft. And as the shaft rotates, it will be connected to the this generator component, and the work is produced. The gas which has expanded from the turbine will go outside as exhaust, and that gas is not recirculated back into the compressor, since there is no connection between the compressor and the turbine. That's why this is an open cycle, and we call it as an open cycle gas turbine. Accordingly, this is the TS diagram of the open cycle gas turbine. So, in the compressor, we follow the part 1 to 2, and since no components are isentropic components or reversible adiabatic components, so that's why we will have to follow the part 1 to 2 dash. So that basically means that from 1 to 2, since we calculate the work done as a function of temperatures, or basically the difference in the temperature between the part to between the part ends, and that's why when the process is isentropic, this is the lowest part that it needs to traverse between the two pressure ranges T1 and P2. Hence, T2 minus T1 is lesser in comparison to the T2 dash minus T1, which the process has to follow because the process is not reversible adiabatic, because there is a heat loss, and that's why to compensate that heat loss, so more amount of work is needed to be done into the compressor. Just imagine that when while compressing a gas, there will be heat produced, and that heat, if we can somehow contain it perfectly inside the compressor, then the exact the heat will be utilized in increasing the this enthalpy of the gas. But what happens is that the heat is not perfectly contained into this compressor as well as in the turbine also, and therefore there is a heat loss. And in order to compensate for the heat loss, because we need the pressure to rise to a particular value that is constant among us, so in order to make that pressure difference possible, we have to apply some extra amount of work in order to compensate for the heat lost. That's why more amount of work is being done while in the compressor due to this irreversibilities, and that's why it has to follow the part 1 to 2 dash. And accordingly, the compressor work input it increases, and the gross work output is basically the turbine. It generates the main power required, and we'll have to subtract the power that is given input to the compressor. So if the negative part negative work is increasing, then the gross power output decreases. Hence the aim is to make it fully isentropic if possible, but generally that is not achievable. We will have certain amount of irreversibilities. That's why we will have to utilize the isentropic efficiency, which is around 80%. We will know get to know about these. Then from 2 dash at elevated pressure at the exit of the compressor, the fuel is supplied to this compressed air, and as it mixes, the ignition happens, combustion happens at constant pressure, and through this constant pressure line, the temperature of the gas increases from 2 dash to 3. That is, the enthalpy increases, and some amount of heat energy is given imparted to the whole mixture, that is the gas at the inlet of the turbine, that is 3. So 3 point at the inlet of the turbine is the maximum temperature achieved throughout the whole cycle, and the gas when it enters into the turbine, it follows again. It has two options to follow: the reversible adiabatic or the isentropic process, that is 3 to 4, or due to the heat losses, the net work that can be recovered between the pressure difference P2 and P1 is less. Yeah, that is, it has to follow a part 3 to 4 dash, and this part is shorter than the part 3 to 4. And as we rely on the temperature difference for calculating the net work, so the temperature difference between 3 to 4 is higher in comparison to 3 to 4 dash. So this could have been uh, harvested from the turbine, but due to the irreversibilities, we cannot get this amount of work. Rather, we'll lose some amount of heat, and the work done will be a little bit less. And that is 3 to 4 dash is the part due to the irreversibilities present in the turbine. And 4 dash is the exhaust of the gas, and you can see that the exhaust of the gas is not means not equal to the ambient air temperature. So the air leaving the gas turbine cycle is at a higher temperature than the ambient. That means that there is some amount of energy still left in the gases or exhaust that could have been utilized to gain the efficiency or to gain the net work output from the gas turbine, but that is left unutilized. So there are certain cycles like regenerative open cycle gas turbine cycles, and where they utilize this heat energy from the exhaust in order to increase the temperature of the uh, a compressed air before the combustion chamber, in order to if that is achieved, if we can give some amount of heat energy before the combustion chamber, then what happens is that the net amount of heat that we need to supply inside the combustion chamber to attain the fixed amount of maximum temperature, that will be less. And if the heat supply is less, then for the lesser amount of heat supply, if you are getting the same amount of work output, then we are at a we are having a higher net plant efficiency. So that is about a method by which this can be increased. So these are the processes which I've already spoken about, and the work input to the compressor, that is T2 dash minus T1. So not T2 minus T1, so T2 dash CP T2 dash minus T1. And heat supply to the combustion chamber, that is T3 minus T2 dash. And CP work output from the turbine, that is CP into T3 minus T4 dash. Then we can calculate the net thermal efficiency, that is here net work output divided by heat supplied. That will be simply the net work output is from the turbine, that is this amount, but we'll have to supply some amount of the work output from the turbine into running the compressor. That's why we'll have to, this is the negative work, and we'll have to subtract this from the net work produced. And so this is the quantity that remains in the numerator, and that is the net work output, and divided by the heat supplied. So the heat supplied is basically raising the temperature from T2 dash to T3, Hence, CP T3 minus T2 dash is the net heat supplied. So this is the net work output, which we have already seen. Then we'll talk about the compressor isentropic efficiency, and it applies the same for the turbine isentropic efficiency. So work input required by in the isentropic compression divided by the actual work required. So if we talk about the work input required in isentropic compression, that is the part follow this 1 to 2, that is less, but due to the heat losses and we need to maintain a particular pressure ratio, we'll have to supply extra amount of work in order to uh, increase the enthalpy of the gases, or we have to compress the gas to P2. So that's why the actual work is higher and the isentropic efficiency is lesser than 100%. So this is Cp T2 minus T1. So Cp T2 minus T1 divided by Cp T2 dash minus T1, and hence if the Cp these are quantities are same, so T2 minus T1 divided by T2 dash minus T1, that is the simple terms. And accordingly we have the isentropic efficiency, because between the same pressure ratio we could have recovered work amounting uh, due to the temperature difference T3 and T4, that is a higher amount of work, but actually we are getting a little bit lesser, that is the actual work output is a little bit lesser, that is T3 minus T4 dash. Hence there is an efficiency associated, and this can be given as T3 minus T4 dash, T3 minus T4 dash divided by T3 minus T4. So that's the entire thing about open cycle gas turbine. That's a very preliminary thing that we should know before solving any problems. Next, I would like to show you how a complete closed cycle gas turbine would look. And by closed cycle, we mean that the same fluid is circulated throughout the entire components of the gas turbine, and the heat addition is given indirectly in the combustion chamber. So we do not have any mixing of the gases, and there will be indirect transfer. So you see this external combustion out here. So from high pressure compressor to the high pressure turbine, there will be external combustion, and due to the external combustion, the amount of heat, amount of temperature that this fluid has, will be increased to T6. So, in a nutshell, what happens is that this is the low pressure compressor, this is the high pressure compressor, and this is the high pressure turbine. What happens is that the low pressure compressor and the high pressure compressor is utilized to get a particular this a higher amount of pressure ratio. But we could have also used one compressor. Why need two, right? That should have been our question. So what happens is that while shifting from low pressure compressor to the high pressure compressor, as you can see here, from 1 to 2, this is in low pressure compressor, and we could have directly gone to this pressure difference. But while doing that, the amount of work that is mm, means we need to supply to this would be very high. As you can see, the pressure lines are diverging towards the right side. So this pressure, the same pressure difference, if we can get in lower in towards the left side, would be less, right? The temperature difference would be less, and accordingly what happens is that the work input that we need to give is would be less. But we have a fixed inlet temperature condition, so we cannot change that. What we can do is that we can cool it, and while cooling it, we can directly get uh, how to cool it. So in the low pressure compressor, when the pressure rises to P2, and after that the air is cooled down to zero point 0.3, and again it is uh, pressurized to pressure P2 at this line. But even if we have gone towards this side, then the net amount of work that needs to be done to compensate for this would be very high, and the intercooling is actually lowering the net work input to the compressor. That's why we need this two compressor arrangements. Sometimes it can be three compressor arrangements as well. So we'll have to see what is our pressure difference, and accordingly we'll have to decide how many stages we will have to use. And there is an intercooler which will cool down the this air or the fluid which is flowing throughout the cycle. Mm, and the high pressure compressor is basically uh, pressurizing to the final pressure value, that is at 4 dash it will be at the final pressure value. And from here we will go through a heat exchanger. So basically heat exchanger is supplying heat to the air, and the heat is supplied from the exhaust gas to the exhaust gas which is going out of the low pressure turbine. So we are utilizing the gas here as well, and that is going into the combustion chamber where indirect combustion, so indirect heat transfer is happening. So there is no mixing of the fuel inside. At the closed cycle gas turbine it is elevated, so 5 to 6 is the heat supplied, 4 to 5 is the heat supplied by the heat exchanger, and 6 to 7 is the basically the process inside the high pressure turbine. But we cannot achieve isentropic processes, so we will have to go through 6 to 7 dash. Then this high pressure turbine is basically connected to the low pressure compressors and the high pressure compressors through the same shaft. So basically the high pressure turbine is responsible for supplying the work to the this compressors, and hence it is completely engaged in that, and there is no work output derived from this high pressure turbine that is useful for driving other applications or producing electricity. Rather, what happens is that from high pressure turbine, the gas which leaves, it is at the state 7 dash. So it is again further heated by external combustion. So heat supply is there. It will elevate the temperature to T8, and further it is pass through a low pressure turbine. So low pressure, why? Because it is operating at lower pressure conditions, and the exhaust which comes out from the low pressure turbine, it goes through here. It is at state T9 dash, and accordingly a net amount of work is being derived from this cycle, and that is utilized in producing electricity or whatever the our objective is. So now we can see that 9 dash is the exhaust gas temperature which is which is leaving the low pressure turbine, and that is at a very high temperature, as you can see here. Obviously the inlet temperature would be 1, and to get to 1 we'll have to go through something, because 9 dash is connected to 1, and the gas will have to go through the same loop and enter into 1, and we cannot release this gas entirely to 1. So what happens is that some part of this heat reduction is utilized in gaining the heat from the compressed state from 4 dash to 5 in this heat exchanger out here, and the other part which is not removed, which is removed by using a cooler out here, and that is extracting the heat, and it is making the cycle to go to 1. So this is a regenerative process, because we are regenerating the heat, and through the waste exhaust gas heat, and we are not we are utilizing the waste, and hence the efficiency will obviously increase, and there is an effectiveness associated with this heat exchangers. What is the effectiveness is that from 9 dash we could have supplied enough heat so that the air loses its heat to the inlet conditions of the cold air, so that is 4 dash. But instead it is not able to supply that amount of heat, and there is a net rise in temperature from 4 dash to only 5. The temperature difference is not same as between the maximum temperature difference we could have got. So that's why there is an effectiveness, and that effectiveness basically say that nothing in this world is perfectly 100%, right? So that's about a complete closed cycle gas turbine. But the processes of intercooling, regeneration, and this combustion, uh, reheating. So these applications I have shown for a completely closed cycle gas turbine. But if we do not connect this exhaust back to the low pressure compressor, so the loop will be open. Accordingly, we will have a complete open cycle gas turbine. So that's the entire concept behind. We will now be solving a few problems. Now this is the first problem, and The problem states this is a quite simple problem, so this is just to brush up and how to do all the other problems. So that is a quite an exercise that we have to do before solving tougher problems. So this problem states that in an air standard regenerative gas turbine cycle, okay, regenerative, uh, emphasis on the word regenerative, the pressure ratio is 5, okay. Air enters the compressor at 1 bar 300 Kelvin and leaves at 490 Kelvin. The maximum temperature in the cycle is 1000 Kelvin. We need to calculate the cycle efficiency. Given that the efficiency of the regenerator and the adiabatic efficiency of the turbine are each 80%, we can assume for air the ratio of the specific heats is 1.4. Also, so we have to show a TS diagram. So let us sink in to this simple problem for 1 minute, and after that I will solve the problem. So let us proceed. So this is a TS diagram of this the process that is stated in this question. So regenerative gas turbine cycle. So basically, the exhaust coming out from the turbine will be utilized in delivering some amount of heat to raise the temperature of the gas coming out from the compressor from 2 dash to 5. So that's the thing. Now, let us solve this problem. So how to solve it? First, we will consider the process. We'll have to calculate the cycle efficiency, right? For cycle efficiency, what we need is, so we need the work input to the compressor, work output from the turbine, and the heat supplied, net heat supplied. If we can get all these three parameters, we can calculate the cycle efficiency. So for getting the work input to the compressor, we'll have to solve for this section. And in here, we are given the pressure ratio is 5, so we will have to first calculate T2. So simply, okay, so here they have gone to the other way. So first we will calculate the for the turbine. So let us calculate for the turbine. We'll have to calculate all anyways. So the turbine, in the turbine, the process will be 3 to 4, isentropic process 3 to 4. So that is, we'll follow this thermodynamic relationship for isentropic process. T3 by T4 equals to P2 by P1 to the power gamma minus 1 by gamma. And eventually we will get the value of T4, which is unknown, because we know the value of T3, that is maximum temperature in the cycle 1000 Kelvin. So we'll get the value of T4, and that is 631.4 Kelvin. But that is not the path that is followed. Actually, the path followed is 3 to 4 dash. So we'll have to find the value of 4 dash, 3 to T4 dash, and we'll use the concept of isentropic efficiency of the turbine. So we'll, for isentropic efficiency, we know T3 by NF T4 dash, T3 minus T4 dash, divided by T3 by T4, T3 minus T4. So that will amount, we know the turbine efficiency 0.8, we only do not know T4 dash. Accordingly, we will find the value of T4 dash out here. So that is amounting to 705 Kelvin. Next, we will find the effectiveness of the heat exchanger. So effectiveness of the heat exchanger is the maximum, sorry, the heat input that is received, the temperature difference of the is that is received with T5 minus T2 dash divided by T4 dash minus T2 dash. That is the maximum possible temperature difference which we could have attained, but we did not attain, rather we have attained this much. So that is the effectiveness of heat exchanger, and the values that we know about is So do we know that? Yes. So for this part, we know that the compressor, it enters at 300 Kelvin and leaves at 490 Kelvin. That's why we do not need to calculate this. So we know T2 dash, and we'll just plug in the values, and we will get the value of T5. So T5 is 662 Kelvin, and till 490 to 662 Kelvin, the heat is supplied by the exhaust gas. So no extra amount of heat needs to be supplied to elevate that amount of temperature. But beyond that, from T5 to T3, we need to elevate the temperature, and that where we need to supply some heat, and that heat we will have to calculate. So first, let us calculate the work consumed by the compressor. That is simply T3 minus T4 dash. No, sorry, work consumed by the compressor. This part, so that is T2 dash minus T1, T2 dash minus T1, and that amounts to 190.9 kilojoule per kg. Then work done by the turbine. So that is T3 minus T4 dash. So T3 minus T4 dash Cp, and accordingly we will get 296.5 kilojoule per kg. Okay, that's good. Next, the heat supplied will be this amount. So T3 minus T5 Cp, and here we will get 339.7 kilojoule per kg. So the cycle efficiency will be net work divided by heat supplied, and net work will be turbine work minus compressor work by heat supplied. Accordingly, we will get 31%, as you can see here. So that is the net cycle efficiency. And mind that here we are only given the specific heat capacity, a specific heat ratio of the specific heats for only air, and we are assuming the specific heat capacity of only air. But in this process 5 to 3, so in this process rather we have to use the specific heat capacity of the gas, combined gas. So if that is given, we will have to use that value. The work consumed by the compressor, here only air is flowing through the compressor, that's why the Cp will be of Cp air, and work done by the compressor, that is Cp will be Cpg out here, Cpg, because the gas is flowing through the turbine. Now there is a question that, so Cp into delta T, so that is basically for a constant pressure process, right? That is basically for a constant process, pressure process. So heat supplied is Cp into T3 minus T5. That is correct because it is in the same pressure line. What about this? There's a change in the pressure. Still, we are using Cp. So the logic behind this is that we assume that the Cp does not change too much. It is not sensitive too much to the change in the pressure. So that's why we can assume a constant Cp even though the pressure is changing. So that's the basic thing. We cannot use Cv because we are calculating the enthalpy difference, not the internal energy difference, right? So in that case, so we have to use Cp. If it would have been internal energy difference, we would have used Cv, specific heat at constant volume. So that is not required. Yes, and if the combustion process here from 5 to 3 would have been in constant volume like that of the Otto cycles, so then we would have used the value Cv, specific heat at constant volume, but now we only have to use the value Cp. So the next question is, a gas turbine plant consists of two turbines, okay, one compressor turbine to drive the compressor and the other power turbine to develop power output, and both are having their own combustion chambers which are served by air directly from the compressor. Air enters the compressor at 1 bar and 288 Kelvin, okay, compressed to 8 bar. So the pressure ratio is 8 with an isentropic efficiency of 76%. Due to the heat added in the combustion chamber, the inlet temperature of gas to both turbines is 900 degrees Celsius. Okay, inlet temperature is same. The isentropic efficiency of the turbines is 86%, and the mass flow rate of air at the compressor is 23 kg per second. The calorific value of fuel is 4200, I think. Okay, anyways, we will see. Kilojoule per kg. We need to calculate the output of the plant and the thermal efficiency if the mechanical efficiency 95% and generator efficiency 96%. So let us think a little bit on this problem, and I will solve this problem after 1 minute. Okay then. So the the whole gas turbine plant will look like something like this. There is only one compressor but two uh, this turbines. One is CT, that is the compressor turbine, and one is the power turbine, which develops the power. And the air is supplied to both through a combustion chamber and from a compressor, from the same compressor. The compressor turbine will be completely responsible to deliver the power to the this deliver the power to the compressor. So let us see to this. the the TS diagram will be something like this. So what happens is that since we are only having this separate power turbine that is not connected to this, and the compressor is supplying the air to this to these turbines separately, we can assume the same cycle for both the cases. Also, we are given that the T3, that is the inlet to the turbines, are same, so we can definitely use these two, and the pressure bar also remains same, right? So this is the TS diagram for either C and CT or C and PT. Both will be the same. And first, we will have to consider the compression process, and we will solve to get T2 dash. So T2 minus T2 by T1 equals to P2 by P1 to the power gamma minus 1, gamma minus 1 by gamma. And accordingly, we'll find the value of T2. But T2 is the not actual temperature, rather we'll have a elevated temperature T2 dash. And we'll for to find out that we have to use the isentropic efficiency of the compressor. So that amounting to T2 dash amounting to 595.4 Kelvin. Next, we'll have to consider the isentropic expansion process initially for the turbine, and with that, the temperature ratio T4 and T3 is related to P4 by P3 by this expression, and eventually we'll find the value of T4, and that is not the actual temperature. We need to find the T4 dash. For that, we will have to consider the isentropic efficiency of the turbine, and that is this. So we plug in the values. We have only one unknown, that is T4 dash, and we will solve it to find T4 dash equals to 759.4 Kelvin. So now we have found the values of T2 dash, T4 dash. We need to calculate the output of the plant and the thermal efficiency. So the plant output will be simply T3 minus T4 dash, Cp into T3 minus T4 dash. So and we'll have to use the mechanical and the generator efficiency as well. So let us see that. So 1 kg of air flowing through the compressor, that is. Hmm. So the main problem here is the main trick here in this question is that we are not known how much amount of air is being passed to the power turbine and how much is needed by the compressor turbine to drive the compressor. But we are given that the total amount of air that is flown through a compressor is 23 kg per second. And based on that, the plant uh, outputs will be different, because that will be in kilowatts. If you need to calculate, we know the in kilojoule per kg, that can be easily found, but in kilowatts that will be different, because it depends upon the amount of mass that is being flown through the turbines. So first we need to calculate the mass which is supplied to the, so if we assume that only 1 kg is passing to the compressor, then how much fraction of it is being delivered to the compressor turbine, and how much fraction? So that will be m percentage will be delivered to the CT, and 1 minus m percentage will be delivered to the PT. Uh, so that part we will have to calculate, and for that, let us see if 1 kg is flowing, then the work done by the compressor will be CPT2 dash minus T1 dash, but that will be not T1 dash, it will be T1. Then the value would be around 308.9 kilojoule, that is kilojoule per kg. And this work will be equal to the compressor turbine, but in the compressor turbine, the work done will be somewhat like M1 into CPG. We'll have to use the specific heat of the gas, right, into the temperature difference, that is T3 minus T4 dash. So M1 into that, and we are neglecting the fuel mass. Although the fuel mass, if the air fuel ratio is around something like 90:1, then the fuel will be 98 times of the M1, which is quite small, and we can neglect that sometimes if not given in the question. Then M1 will be amounting to 0.662 kg. So out of 1 kg, 0.662 kg is going into the CT turbine, the compressor turbine, and the rest, that is 0.328 kg, will be going to the power turbine. So in order to calculate the power output, we have to calculate the work done by the PT generator. So that will be 1 minus m into CPG T3 minus T4, that is per kg of gas, per kg of total gas to the compressor, that is 157.7 kilojoule. Now we will convert that into watt. How? So 23 kg per second is being delivered. Out of that, 1 minus m or 0.338 is being percent is utilized in the power turbine. So simply we will multiply with the 23 kg per second, and the efficiencies associated, the mechanical efficiency and generator efficiency. So that is 3307.9 kilojoule per second, and that will be kilojoule per second. So simply kilowatts. It will be simply kilowatts. So next, we need to calculate the thermal efficiency. So for that, we need the heat input. The heat input will be CPG T3 minus CPA T2 dash. So let us see why. So T3 out here. So CPG T3, that is the enthalpy of the gas entering the turbine, minus the CP T2 dash. So CP22 dash CPA. Now why these are different? Because the T2 in the here T2, the enthalpy would be CPA into T2 dash, and after mixing with the gas, the enthalpy is raised to CPG into T3. So that's where the input will be, and if we put in the values, we'll get 724.7 kilojoule per kg of air. Then we calculate the thermal efficiency. The thermal efficiency is given by simply work output by work input. So we'll consider this value. So whichever value you calculate, because that is the simple 23 times of that, and so we need the thermal efficiency of the not of the plant, rather of this whole cycle. So we will consider that value, and we'll get a value of 21.76%. So this is the next question. A is drawn in the gas turbine unit at 15 degrees Celsius and 1.01 bar, and pressure ratio is 7:1. The compressor is driven by the HP turbine, and the LP turbine drives a separate power shaft. The isentropic efficiencies of the compressor and the HP and LP turbines are 0.82, 0.85, and 0.85 respectively. The maximum cycle temperature is 610 degrees Celsius. Calculate the pressure and the temperature of the gases entering the power turbine. The net power developed by the unit per kg per second mass flow, and the work ratio and the thermal efficiency of the unit. When to neglect the mass of the fuel, assume the following: for compression process, CPA value, gamma values, and combustion separate CPG and gamma value. So let us take a minute to think about this question. Okay, so let us start solving this question. So this is how the power plant will look like. Then, the high pressure turbine is responsible for only giving power input to the compressor, and the exhaust which is coming out from the high pressure turbine is actually driving through the low pressure turbine, which is responsible for getting the network output. This is the TS diagram, and we will start solving. First, we will solve for the pressure and temperature of the gases entering the power turbine, that is P4 dash and T4 dash. So that will be amounting to, so we'll use the isentropic compression process in in the compressor part. So in here we will we have the value of T1. We know the value of the entire pressure difference, that is 7.07 bar to 1.01 bar. And next we will calculate the value of T2. Then for calculating the value of T2 dash, we will utilize the isentropic efficiency of the compressor, T2 minus T1 divided by T2 dash minus T1, and that is amounting to T2 dash will amount to 549.6 Kelvin. Next, we will calculate the compressor work, so that is CPA into T2 dash minus T1, and we will get the work output to be 262.9 kilojoule per kg. So this amount of work is completely utilized by the HP turbine, right? And of the HP turbine, what do we know? We know that maximum cycle temperature is 610 degrees Celsius. So this T3 we know, and for T4 or T4 dash we do not know. So we'll simply equate these. So the HP turbine work and the compressor work are equal. So in that we will equate this. We do not know T4 dash. We solve for T4 dash and we'll get T4 dash to be 654.4 Kelvin. We know T4 dash, but we do not know what is the pressure of this intermediate part. So in order to calculate the pressure, first we need to calculate the temperature if this process would have been isentropic. So T4. So in order to get this T4, we have to consider the isentropic efficiency of this part turbine, HP turbine. And yeah, so the one of the question is that the pressure and temperature of the gases entering the power turbine. So the temperature we have got, that is 65.4 Kelvin. We now need to calculate the pressure. So in order to calculate the pressure, we'll utilize the isentropic efficiency of turbine. Here we know the value of T3, we know the value of T4 dash. We do not know the value of T4, so we'll solve for T4 and we will get T4 equal to 614 Kelvin. Now the isentropic efficiency, isentropic expansion process T4, If we consider, then T3 by T4 equals to P3 by P4 to the power gamma minus 1 by gamma. Now we do not know the value of P4, rather we know all the values of P3, T3 and T4. So we'll solve for P4 and we will get P4 equal to 1.636 bar. Okay. So the pressure of the gas entering the power turbine is 1.636 bar. So we have solved for the first part. Then the second part is net power developed by the per kg per second mass flow, that is P. So for that we have to calculate the network output, the network input, and from that we can calculate. So we have to now calculate T5 dash. Why need to calculate T5 dash? Because we have to calculate the work output, and nowhere it is given what is the exhaust temperature of. So in order to calculate that, we now know the pressure difference, the pressure ratio we will get to know from here, and we know the value of T4 dash, so we will get the value of T5. So simply we will get the value of T5 to be amounting to 580.6 Kelvin. T5 is 580.6 Kelvin out here. Then for the low pressure turbine, we will use the isentropic efficiency, and from that value we will get the value of T5 dash. So you see how. So T5 dash is equal to 591.7 Kelvin. 591.7 Kelvin. Next, we will calculate the work done by the low pressure turbine, that is CPG T4 dash minus T5 dash, and it will be amounting to 72.1 kilojoule per kg. And since the low pressure turbine is the only component which is generating the power from net power from this power plant, so we will use this. This is the amount of work that is being developed per kg per second. And if we consider 1 kg per second, we'll simply have to multiply into this, we'll get 72.1 kilowatt. That is the answer. Next is the work ratio. So work ratio, we know work ratio equals the net work output divided by gross work output. So that is amounting to 72.1 divided by 72.1 plus 262.9. So gross work output will be this high pressure turbine work divided by low pressure turbine work, that is the net gross work. But the net work is only derived from this low pressure turbine, so that is the net work. And accordingly, we have the work ratio 0.215. So the purpose of calculating the work ratio is that it will tell you that how much percentage of the total work derived in the gas plant is being used to produce electricity or whatever we want to use with the power. So that is only 21.5% of the entire work derived from this turbine is being utilized to calculate to means get the power output. Next, we'll calculate the thermal efficiency of the unit. So the thermal efficiency we have to calculate. For thermal efficiency we have to calculate the heat supplied, and the heat supplied will be given by the temperature difference of T3 minus T2 dash and into the CPG. So that is equal to 383.4 kilojoule per kg. Next, we need to find the total efficiency, the net work output divided by heat supplied, that will be amounting to 18.8%. So that's the answer, and we'll move on to the next question. That is, the pressure ratio of an open cycle gas turbine plant is 5.6. Air is taken between 30 degrees Celsius and 1 bar. The compression is carried out in two stages with perfect intercooling in between. The maximum temperature of the cycle is limited to 700 degrees Celsius. Assume isentropic efficiency of each compressor stage as 85% and that of turbine as 90%. Determine the power developed and the efficiency of the power plant if the airflow is 1.2 kg per second. The mass of fuel may be neglected. It may be assumed that Cp equals to 1.02 kg per kilojoule, kilojoule per kg Kelvin, and gamma equal to 1.41. So let us take a moment So answer this question, analyze this question. Okay, then let us solve this question. So these are the inputs that we are given, and this is the TS diagram that we can uh, have. So it is told that we have compression in two stages with a perfect intercooling. So the stage one is the 1 to 2. So this part is compression, and the 1 to 2 dash, and the air in 2 dash part is cool down to 3, which is again equal to the T1. So the compressed air is at an elevated pressure, but it is temperature is cooled down to the ambient temperatures, and ambient temperature means the temperature of the inlet. And again, from 3 to 4 dash, the compression is occurring in the second stage of the compression part. And final, the compressor the compression is from 1 bar to 5.6 bar. So the pressure ratio is 5.6. So we will first calculate for the power developed and efficiency of the power plant. So power developed is we can first we will have to calculate what is the work output from also work input required in the two stages of the compressors P2 and P1. So first we'll find the P2 P1. So if it is perfect intercooling, then the P2 by P1 equals to P4 by P3 equals to P4 by P1. No, means the entire pressure ratio to the power half. So square root of the entire pressure ratio. So that we can find, and this is the case of the perfect intercooling. So both compressors have the same inlet and the inlet temperatures. Same inlet temperature T1 equals T3 and T2 dash equals to T4 dash. The pressure ratio and the isentropic efficiency of each compressor is same, right? So that's why the work input required for each compressor will also be same. So we need to calculate for only one part, and the other would have the same work. So we consider the isentropic process 1 to 2, and from here we find the temperature T2. Then we use the isentropic uh, efficiency of the compressor, and we find the difference between T2 minus T1 and T2 minus T1 divided by T2 dash minus T1. Accordingly, we will find that T2 dash will be equal to 404.4 Kelvin. Next, the work input to the two-stage compressor is 2 into mass into Cp T2 dash minus T1. Accordingly, we will have the net work input required to the compressor is 248.32 kilojoule per second. For turbine part here, turbine part, we'll have to calculate again. We do not know the exhaust temperature, so we'll have to find first the isentropic the temperature if the process would have been isentropic. So that would be T6 589.7 Kelvin. So this is T6. Then we'll calculate the for T6 dash the actual exhaust temperature by utilizing the isentropic efficiency of the turbine, and from here we will get T6 dash to be 628 Kelvin. This is 628 Kelvin. Next, the work output of turbine would be amounting of due to the resultant temperature difference between T5 and T6 dash, that is m into Cp into this, and eventually we will get the work done by the turbine is 422.28 kilojoule per second, out of which 248.32 kilojoule per second is utilized by the compressors. So the net work output would be 173.96 kilojoule per second or kilowatt. Then this is the network output. We need to calculate the efficiency of the power plant, so we need the heat input. So the heat supply will be mcp T5 minus T4 dash. That will be simply amounting to 695.92 kilojoule per second. Then uh, the power plant efficiency will be only 25% in this case. So that is the end of this question. The fourth question of this session. Next, we will solve the other question. That is the next question would be a conceptual question. That is, why are the back work ratios relatively high in gas power plants compared to those of steam power plants? So by back work ratios, we actually mean, so we are comparing between gas turbine power plant and steam power plant, and we are concerned about the back work ratio. So the back work ratio is the ratio of negative work to the turbine work in a power plant, and the negative work we know that is the work required to drive the compressor, and that is given by the formula minus VDP divided by turbine work, and minus VDP is the work by the compressor in case of gas turbine, and VDP is the work uh, required to drive the pump in case of steam power plants, and that is the negative work in either compressor or pump. Then if we consider a gas turbine and a steam power plant, so first we have to know how these power plants operate. So we already know how a gas turbine operates. So that is the compressor section. Air enters the compressor, gets elevated to a particular pressure, then it goes into the combustion chamber. It receives some amount of heat input. It elevates to a temperature like T3 with the highest amount of enthalpy. That enthalpy is utilized in generating the work output from the turbine by expanding the gas, and the rest of the gas is going through the exhaust. So that is of a gas power turbine power plant. But in a steam power plant, what we have is, first we have a boiler. In the boiler, heat is added to the water which is present in the boiler, and the steam is produced. The steam has very high enthalpy, and that high enthalpy steam is uh, sent to the turbine, and in the turbine the steam, it drives the enthalpy is delivered to the turbine blades, so which rotates the turbine blades, and the work is recovered from the turbine as the steam expands. And when the steam expands, it goes either to uh, still a superheated state or a wet state at a lower temperature, lower pressure, and that lower pressure steam is going into the condenser, where the condenser will remove the excess amount of heat enthalpy from the steam, and accordingly this steam will return back to its liquid state, that is water, and that water is again pumped to the boiler using a pump. So the in turbine the work is recovered. It is for the entire power plant, but some amount of work is required to drive this pump, and this pump, the work in the pump is basically the negative work minus VDP. Now let us look at a power plant. So you will have that in gas turbine power plants, air is compressed from turbine exhaust pressure to the combustion chamber, and the work is given by minus VDP. Now the thing about gases is that, air is that the specific volume of air is very high. So the VDP, the V means the specific volume of air, is quite high even in the closed cycle gas turbine power plant. So for the same pressure difference, if you have a specific volume of air very high, then the compressor work is required is very high, and also the bulky compressor is required. So that's the case, but in the steam power plants, the specific volume, so the pump is responsible for pumping the water to a higher pressure. So the fluid passing through the pump is basically liquid, and for liquid, we know that the specific volume is less. Hence, hence, the pressure in the condensator is raised to boiler by condenser extraction pump and the boiler feed pump in series. Okay, and the specific volume of water is very small compared to that of air. Hence, the pump work is also small, or the negative work is also small. If this negative work is small, then the back work ratio is also small. So that's why, for these reasons, the backwork ratio of gas turbine plants is relatively high in compared of the steam power plants. So that was the concept behind the backwork ratio, and we require very low amount of backwork ratio in order to have higher efficiency or higher specific work output. Next is the question: in a gas turbine plant, compression is carried out in two stages with perfect intercooling and expansion in one stage turbine. If the maximum temperature T max Kelvin and minimum temperature T min Kelvin in the cycle remain constant, then we need to show that for maximum specific output of the plant, the optimum overall pressure ratio is given by this formula. So we are given that the maximum specific output of the plant. We are given the constants maximum temperature and the minimum temperature. We are given the constant that is a perfect intercooling. Then we have to show the maximum specific output of the plant. For in order to get the maximum specific output of the plant, the optimum overall pressure ratio is given by this. So in order to solve these questions, what we have to do is that we have to get a particular specific output of the plant, we, based on these conditions that we have, the perfect intercooling, Tmax and Tmin. So we'll have to get this maximum specific output of the plant. In order to maximize it, we'll have to differentiate with respect to the variable we are concerned. Right. Then uh, on doing that, we'll get what is the equation of the variable. So you just think about it for a minute, and I will solve this question in a while. Okay, then. So this is a particular, and this is the TS diagram we are concerned about. So this is having compression in two stages with perfect intercooling. So the temperature T3 and T1 will be same. Also, the pressure ratios will be same, and that pressure ratios will be the square root of the entire pressure ratio, right? That is the condition of the perfect intercooling. And there is only one turbine. So we'll have to assume that the optimum pressure ratio in each stage of the compressor is root R. So if R is the pressure ratio between this the fifth point, so let us assume this is the P5 and this is P1. So P5 by P1, that is the entire pressure ratio R. Okay, then the optimum pressure ratio in each of these cases, not optimum, but the pressure ratio in all these cases will be the square root of that, square root of P5 by P1. So, okay. Anyways, so T2 by T1, so this is the isentropic relationship, and P2 by P1, we now know that is root R. So we'll just simply put in the values. That will be gamma minus 1 by 2 gamma. And then work done by the compressor is 2 Cp T2 dash minus T1 for both compressors. Then we simply use the isentropic efficiency part. So T2 dash minus T1, T2 dash minus T1, that will be T2 minus T1 divided by eta EC. So that is also given out here. So that will be higher compared to T1 minus T2. That's we divide by a lower quantity. So that makes sense. And 2, why 2? Because the work done would be same for both these compressors, because the efficiency associated with both these compressors are same, the pressure ratio is same. That's why the this will be simply 2 into of that. Then we take T1, that is the minimum temperature out, then T2 by T1 will be remaining, and accordingly we'll have T2 by T1, that is R to the power gamma minus 1 by 2 gamma minus 1. That part is coming. Next, T5 by T6 for the turbine part. So that will be again R to the power gamma minus 1 by gamma, T5 by T6, and eventually we will find T6 to be T max, that is T5, T max to the power R to the power gamma minus 1 by gamma. So we have the work done by the turbine Cp equals to T5 minus T6 dash. Then we simply plug in these values. Then we will get T5 to be T max and T6 dash to be T max divided by that this amount into the eta T. Why eta T? Because T5 T5 minus T6 dash, T5 minus T6 dash is the lesser amount. So in order to get a higher efficiencies, we'll have to get T5 minus T6, that will be equal to eta into T5 minus T6 dash. So that's why eta T is coming. And we will finally get the work done by the turbine will be CPT max into this entity. So finally you will find that work net would be work turbine by work compressor, and we have found the work done by the turbine, we have found the work done by the compressors. We'll calculate the network. So network would be, if we plug in the values, we will get this is the expression of the network, and our objective is to uh, maximize this work, right? Maximize this work with respect to R. R is the variable out here. So for maximum work output, we will have to get dW net divided by dr equals to 0, and we will get this particular equation, and on simplification we will get eta EC eta T into eta C, T max divided by T min equals to R to the power 3 gamma minus 1 divided by 2 gamma, and accordingly we will get the optimum pressure ratio to be this. Hence proof, and in this way you will have to prove such kind of derivation type problems. Next question, it says that in a gas turbine the compressor takes in air at a temperature of 15 degrees Celsius and compresses it to 4 times the initial pressure, so pressure ratio is 4 with an isentropic efficiency of 82%. The air is then passed through a heat exchanger heated by the turbine exhaust before reaching the combustion chamber. In the heat exchanger, 78% of the available heat is given to the air. The maximum temperature after constant pressure combustion is 600 degrees Celsius and the efficiency of turbine is 70%. Neglecting all losses except those mentioned and assuming the work fluid
throughout the cycle to have characteristic of air, find the efficiency of the cycle. So we need to find the efficiency of this cycle. So let us take a minute to think about this question. Okay, then let us solve this problem. So the TS diagram will something look like this. So simply uh, we have a this compressor and we have a gas turbine, and the heat supplied is divided into two parts. One is the heat supplied is supplied from the exhaust, and the second part is supplied using fuel. So we'll only have to utilize the heat supplied based on this for the thermal efficiency part, and we need to calculate the work input and the work output, and that way we can solve this problem. So simple. The previous case, we first consider this compressor part. We know the value expression for getting T2, and that is T2 equal to 4828 Kelvin. Then we'll use the compressor efficiency and we will get the value of T2 dash. The T2 dash will be equal to 459 Kelvin. Then we'll have to consider the isentropic expansion process T4, and T3 divided by T4, that part, it will amount to 587.5 Kelvin. The eta turbine would be, so here we have calculated this T3, T4, so we have calculated T4. We need T4 dash, so we'll utilize the efficiency of turbine and finally get the value of T4 dash to be equal to 673 Kelvin. Then we have to calculate the compressor work. That is Cp T2 dash minus T1, T2 dash minus T1. But we do not know the value of Cp, but we are given the value of R and we are given the value of gamma. So this is a new trick. So we know this thermal this part. So Cp equals to gamma R by gamma minus 1. And if we need to calculate Cv, that would be R by gamma minus 1. So that way you can calculate the value of Cp, and the Cp value comes out to be 1.0045 kilojoule per kg Kelvin. Finally, the work of compressor will get 171.7 kilojoule per kg. Next, we'll calculate the work done of turbine. We use the same Cp value, but the temperature difference is now T3 minus T4 dash out here. Then it would be given 200.9 kilojoule per kg. So the net work done would be work turbine minus work compressor, and after subtracting, we'll get only this much amount, that is 29.2 kilojoule per kg is available for derived from the entire gas turbine power plant. Then we'll calculate the effectiveness of the heat exchanger. So we are given the effectiveness, we need to calculate the value of T5 in order to see how much is the heat supplied, that is T3 minus T5. For that, we use the value of effectiveness, that is T5 minus T2 dash, T5 minus T2 dash, so we know the value of T2 dash, T4 dash minus T2 dash, so we know the value of T4 dash and T2 dash. So we will simply have to solve for T5 and we will get the value of T5 to be 626 Kelvin. Then we need to calculate the heat supplied by fuel per kg. So that is T3 minus T5, simply T3 minus T5 into Cp, and we will get 248.1 kilojoule per kg. So the cycle efficiency will be net work done divided by heat supplied by the fuel, and we will get 11.7%. So the way of solving all these problems is quite the same.
So you just have to be consistent with all the parts, what you have and what you need to calculate. If you can simply think on that, you will be able to solve these problems. So we will move on to the next question. That is, a gas turbine employs a heat exchanger with a thermal ratio of 72%. The turbine operates between pressures of 1.01 bar and 4.04 bar. The ambient temperature is 20 degrees Celsius. The isentropic efficiencies of the compressor and turbine are 80% and 85%. The pressure drop on each side of the heat exchanger is 0.05 bar and a combustion chamber 0.14 bar. So this is a different type. We have a pressure drop associated with the heat exchanger and the combustion chamber, right? So that is a new thing. So we assume that the combustion efficiency to be unity and the calorific value of the fuel to be 4100 41,800 kilojoule per kg. We need to calculate the increase in the efficiency due to heat exchanger over that for simple cycle. The value of Cp is constant throughout and is equal to 1.024 kilojoule per kg Kelvin, and assume gamma to be 1.4. For simple cycle, the air fuel ratio is 90 is to 1, and for the heat exchange cycle, the turbine entry temperature is same as that for a simple cycle. So we need to calculate the increase in the efficiency due to the heat exchanger over a simple cycle. So that is an interesting question, and we are given there is a pressure drops in the heat exchangers and the combustion chamber. So if we use a heat exchanger, there is a drop in the pressure. That will not be beneficial, but what is the overall impact we have to see. So let us take a minute to sink into this question. Okay, then let us solve this question. So this is the TS diagram, and this is the TS diagram of a simple cycle. So in a simple cycle, we only have a combustion chamber. So this is the compressor part, and from compressor, this is generally the it is compressing up to 4.04 bar, but there is a pressure loss to 3.9 bar. Why 3.9? Because there is a pressure loss of 0.14 bar. So there is a loss to 3.9 bar in the combustion chamber that you can see out here, and from that it is going to the turbine, and there is it is releasing its exhaust to the ambient, that is 1.01 bar. So that is the simple cycle, and for a simple cycle we know how to calculate. So for the compressor part, so we calculate for the value of T2. The T2 will be 435.4 Kelvin. Then we use the efficiency to calculate the value of T2 dash. So the value of T2 dash will be 471 Kelvin. Then uh, we have to calculate the value of T3, I guess. Yes, the value of T3. So we know the value of T2 dash, and we know how much is the fuel that is coming. So the air fuel ratio is given 90 is to 1. So the amount of fuel per kg of air is 1 by 90, and we have given the calorific value, and we have assumed the mass of air to be 1 kg. Then for 1 kg of air, what should be the value of T2 dash? So that um, T2 dash will be, sorry, T2 dash is known. T3 will be around 919.5 Kelvin.
So T4 by T3 equals to P4 by P3 to the power gamma minus 1 by gamma, and T4 into equals to 625 Kelvin. Finally, turbine efficiency of the turbine is T3 minus T4 dash divided by T3 minus T4, and so T4 dash equals to 669 Kelvin. And finally, we will find what is the T4 dash. So in here calculating, we have taken the value of the pressure P3 to be 3.9 bar, not 4.04 bar, because we had to account for the loss in the pressure in the combustion chamber. So that is T4 dash. Next, we will calculate the thermal efficiency of the simple cycle. So in the simple cycle, we are known what is the output, what is the input of the work, what is the heat supply. And based on that, we simply plug in the values of temperatures, because we have to take the specific heat of air equals to specific heat of gas, because no information is given, and eventually we will get the thermal efficiency is 16.16% for the simple cycle. Next, for the heat exchanger cycle, the thing gets a little bit different. So this will be a heat exchanger cycle. Eventually this heat exchanger was not present, and now before entering into the combustion chamber, there will be heat exchanger part, and uh, due to this heat exchanger, there will be a pressure loss in this also, and the pressure loss would be 0.05 bar, 0.05 bar, and there is a pressure loss of 0.14 bar as well in the combustion chamber. So we'll have to account for these two pressures, hence the net pressure would be 0.385 bar now. And again, as the exhaust is coming out from this turbine, so the exhaust will go through this heat exchanger and before liberating into the ambient. And that's why the ambient is having 0.01 bar, and we'll have to consider that there will this pressure is achieved after accounting for the loss in the heat exchanger of the exhaust gases. That's why we'll have to add up this pressure out here. So the pressure in P3 will be 4.04 minus 1.4, that is a combustion chamber, and this is for the heat exchanger, the 3.85 bar. But here P4 will have to raise it by 1.06 bar. Why? Because eventually in the after moving to the heat exchanger, it should lower down to 1.01 bar. So it will have to lower down after accounting for the loss, yeah, pressure loss, and that's why the P4 should be higher at 1.06 bar. Then we'll use the same part for the gas turbine out here. We know the P3 and we know the P4 dash or P4, and we know, do we know the value of T3? So we'll see. So T4, T3, we know the value of T3, that is for the same, means the cycle is same. So the T3, um, the temperature would be the same, so 990.5 Kelvin, and we'll multiply with a factor of 0.69, and we will get the T4 value to be 634 Kelvin. Then we'll use the efficiency part and we'll calculate the actual temperature, that is T4 dash, which is 667 Kelvin. And from that, so we can, from this we can calculate the work done in by the turbine now after installing the heat exchanger, and that will be a little bit less because the pressure difference is a little bit less. But again, we'll have to account for a net heat supplied by the exhaust, which is reducing the amount of heat we need to supply from by using fuel. So that will actually increase the thermal efficiency, and we'll have to find how much is the heat that we need to supply after this installing the heat exchanger. So for that we need to find the value of T5 out here. So we'll use the concept of effectiveness of the heat exchanger out here. So the effectiveness or the thermal ratio will be T5 minus T2 dash, that is the heat gain, by the T4 dash minus T2 dash, that is the total amount of heat that was available to be gained by the this air. So from here we only need to calculate the value of T5, and the T5 value ends up to be 619 Kelvin. So finally, the ether thermal, considering uh, s- this heat exchanger and for this regenerative heat cycle, also accounting for the pressure losses. So finally, we'll find the ether thermal to be 21.46%, which is higher than the simple cycle by 5.3%. So by installing the heat exchanger, although we're accounting for additional pressure losses, but the final this output and the efficiency is increased by 5.3%. So we that's a viable method. So the next question is this is the last question of this today's session, and this question is states that of 4500 kilowatt gas turbine generating sets operates with two compressor stages. The overall pressure ratio is 9:1. A high pressure turbine is used to drive the compressors, and the low pressure turbine drives the generator. The temperature of the gas at entry to the high pressure turbine is 625 degrees Celsius, and the gases are reheated to 625 degrees Celsius after expansion in the first turbine. So the inlet to the turbines, both the turbines are the same. Then the exhaust gases are leaving the low pressure turbine are passed through the heat exchanger to heat the air, leaving the high pressure stage compressor. Okay, so that's why it's having a mm, to heat the air, leaving the high pressure stage okay, so there is a regenerative process as well. There is a heat exchanger, and the compressors have equal pressure ratios, and intercooling is complete between stages. The air inlet temperature to the unit is 20 degrees Celsius. The isentropic efficiency of each compressor stage is 0.8. The isentropic efficiency of each turbine stage is 0.85, and the heat exchanger thermal ratio is 0.8. The mechanical efficiency 95% can be assumed for both power shaft and the compressor shaft, neglecting all pressure losses and changes in the kinetic energy. We need to calculate the thermal efficiency, work ratio pumped, and mass flow in kg per second. So we have to neglect the mass of fuel and assume the following. And let us take a minute to understand this question properly, and after that we will solve this question. So let us start solving this question. So this will be the net uh, uh, look of the gas turbine power plant. So this is the low pressure compressor, this is the high pressure compressor, and these are connected through an intercooler stage. This is the TS diagram where it is shown the intercooling is perfect. That's why the air inlet to the low pressure compressor is equal to the air inlet to the high pressure compressor. So there is a cooling stage which cools the temperature of the air at elevated pressure from 2 to 3, 2 dash to 3. Then from the high pressure compressor, the air enters into a heat exchanger where heat is exchanged between the exhaust of the low pressure turbine, and some enthalpy is raised, of the air that enters into the combustion chamber, primary combustion chamber, before the high pressure turbine. So the high pressure turbine here is responsible for driving both the low pressure and the high pressure compressors, and then the exhaust from the high pressure turbine is again reheated in the combustion chamber to an elevated temperature, the same temperature T6 and T8, and after that it is expanded in the low pressure turbine, which is producing the net work from this entire cycle. And the exhaust is again going into the heat exchanger, as you can see out here, and finally it is released to the ambient. So here is the T6 T7 is basically the process happening in the high pressure turbine. 6 to 7 dash, and then again 8 to 9 dash is in the low pressure turbine. And from 9 dash it is going to 10, so it is losing that amount of heat, and while supplying that amount of heat to T4 dash to T5. Now if we talk about the thermal efficiency, the pressure ratio and the isentropic efficiency for each of the compressor is same, and then the work input required for each compressor is also same because of the perfect intercooling. So we need to only calculate the work for only one of the compressors, then we'll multiply with two. So T21, we'll have to first find the isentropic value, isentropic temperature value. No, sorry, the temperature for the isentropic process T2 out here. So for we'll consider the pressure ratio. The overall pressure ratio is 9:1. So for each of these processes, the pressure ratios will be root over 9. So root over of that, so pressure ratio will be 3, 3. And in that way, we find the value of T2, that is 401 Kelvin, and we'll use the efficiency of the low pressure turbine and finally get the value of T2 dash, that is 428 Kelvin. So when we know the T2 dash and 1, we can calculate the work done from the compressor and multiply by 2 to get the entire work input required by the compressor. So this is first stage, that is 135.6 kilojoule per kg. Then the high pressure turbine is responsible for driving the both the low pressure compressors and also to overcome the mechanical friction. That's why the total work output of the high pressure turbine is given by 2 into this work input of the compressor divided by the mechanical efficiency of this particular shaft. So that is 0.95, and that amount of work that is derived by the HP turbine. So using that, we calculate the value of T7 dash, because T6 we know that is the maximum temperature, that is 625 degrees Celsius. So T7 dash we will get to know from here, but we do not know the pressure difference here. So for that we'll have to calculate what is T7, and to calculate T7 we consider the isentropic efficiency of the high pressure turbine, and finally we find the value of T7 to be equal to 606 Kelvin. So we know now the value of T7, we now know the value of T6. So we know the value of P, do we know the value of P9? Sorry, the pressure out here. So, but we know the pressure, total net pressure ratio. So we'll utilize that. You see how. So T6 by T7 is equal to this P6 by P7 to the power gamma minus 1 by gamma, and from here we get the value of P6 by P7 to be 4.82. Okay, then P8 by P9, P8 by P9 we can directly calculate from this. So this is around P6 by P9, and we divide by P8 in both. So P6 by P8, that is equal to P6 by P7, and we know that 4.82 into P8 by P9 equals to 9. So that's how we will get the value P8 by P9 equal to 9 by 4.82 equals to 1.86. And we only know, we need to know about the pressure ratio. Then we'll calculate what is the actual temperature T9 dash. So T8 we know, how we know T8, because T8 is 625 degrees Celsius. So are reheated to 625 degrees after expansion from the first turbine. So again reheated to 625 degrees Celsius. So from that we calculate T9. So T9 is 774, but we need the value of T9 dash. We use the isentropic efficiency of the turbine, low pressure turbine, and we find the value of T9 dash to be equal to 792.6 Kelvin. So we now know the this is the temperature of the exhaust from the low pressure turbine. Then the net work output will be simply the work derived from this turbine. So CPG into T8 minus T9 dash into 0.95. Why 0.95? Because that is the mechanical efficiency, and we'll get a value of 115.15 kilojoule per kg. Then the thermal ratio, the effectiveness of the heat exchanger, we use in order to find the value of T5 out here. And rest all known, we can solve for T5 and we'll get T5 to be 719.7 Kelvin. Okay. Next, the heat supplied will be equal to total heat supplied over this region and total heat supplied from this region in the combustion chambers. So T6 minus T5 into CPG and T8 minus T7 dash into CPG. And accordingly, you will find the value to be 490.2 kilojoule per kg. So if we know all this, we can calculate the thermal efficiency, the net work output by heat input, and we will get the thermal efficiency to be 23.5%. That is the first part of the problem. Then in the second part, we have the work ratio. The work ratio can be calculated first by calculating the gross work of the power plant. That is the work derived from both of the turbine and turbines, and it will be amounting to 406.7 kilojoule per kg. Then we calculate the work ratio to be net work output divided by gross work output, and it will be 28.3% or 0.283. That is the answer, work ratio. Finally, we calculate the mass flow in mass flow rate. So if we assume that the mass flow is m, then m into 11 point sorry 115.15 kilojoule per kg, that will be amounting to 4500 kilowatt, right? So that is 4500 kilowatt. So if that is the case, that m would be 39.08 kilojoule per kg per second, and that amount of air needs to be supplied to the compressor part in order to get that amount of this power. So we have neglected the mass of air gases, so we need not calculate that because the airflow ratio is not given out here. But if the airflow ratio would have been given, we can calculate more precisely what is the amount of air that is required. So this was the questions which are discussed regarding the open gas turbine problem solving session today, and these were a little bit tougher than the previous questions that we have solved in the session previous to this. So these videos are available in YouTube, so you can just um, uh, check the links in the uh, Google file that is being uploaded in the website of the NPTEL this course, and while clicking you will get all the video informations. Also this video will also be uploaded, so you can look at it anytime you want, how many times you want, that's up to you, and you are free to choose your pace. But the thing is that the main motive is that we need to gain some confidence in solving the problems related to gas turbine. And now I feel that, I hope that we are a little bit more confident than previous in solving open cycle gas turbine. We now know how to utilize the concepts of intercooler, then regenerative cycles by using a heat exchanger, then again reheating between two turbine stages. So we now know all of these concepts, and we also have learned how it is a little bit different from the steam power plant, and uh, what is the back work which is associated with these power plants and how it is different from a steam power plant and a gas turbine power plant. So that we have also learned in this session. So I would like to thank you all for attending this lecture and hope to meet you again in the next week. Okay then, thank you. Bye bye.